Hello, apologies for that. We had a slight audio issue there. Hopefully everyone can now hear me. Hi and welcome to today's session. We're going to be talking about moments and resistive forces today. So it's going to be a kind of web class. So we're gonna learn some new material. We're going to learn some things about moments, and we're going to learn some things about resistive forces. And for each of those halves, once we've learned some stuff, we'll do some exam questions just to check how we're doing and to check that we're understanding these concepts. So today's going to be in two halves. And we're actually going to start with resistive forces. Okay, so hopefully everyone can hear me okay now. Great. Yeah, I see you can. Okay, so sometimes we'll be going through content, we'll be learning new stuff. And when we're learning new stuff, just let me know in the chat if you have any questions. And if I have time, then I'll absolutely try and answer them. And I'll probably ask things as we go along as well. And if you know the answer to the thing I'm asking, pop it in the chat, and then I can see if people are following. Okay, awesome. So I think we're really in a position to get started. So welcome again to the web class. This is Moments and Resistive Forces. This is me. I'm Matt, lead physics teacher here, and have been tutoring physics now for about 6 years. Some of those years here at Snap Revise. All right, and today is about moments and resistive forces. So we're going to start with the resistive forces bit. We are going to explain the effects of resistive forces on bodies in motion. We're also going to define moments and centers of mass. So that's going to be in the second half. And we're going to determine if systems are in rotational or translational equilibrium. So we're often used to the idea that equilibrium means having no resultant force, but we're going to talk about rotational equilibrium, where we also talk about having no resultant moment. Okay. So let's get started. And usually the way we like to get started is just by reviewing a few things that are going to be handy to know for today's session before we do the main learning. Hi there, nice to meet you. Hopefully it's a good class for you. All right, so I'm going to ask you a couple of things just to get us warmed up. A really key concept today in both halves is going to be Newton's second law. So as an equation, can anyone tell me what Newton's second law says? I'll tell you it's something about the force. Good, yeah, okay. So Newton's second law says F equals ma. Good. And one of the key things, especially today actually, is to know what we mean when we talk about this F. So what is this F? Is this any force on our object? The resultant force, exactly. There can be many forces on an object, like the many forces that we're looking at here on this object. However, it is the resultant force which is equal to ma. I'm just going to pause this for 1 second. We actually seem to be having a slight technical issue with my pen. So just hold with us for 1 second, and I'm going to try and sort this out. Okay, apologies for this, everyone. We'll be back in just a second. In the meantime, just put down in the chat, how do I add forces if I can write them as arrows? How do I add them? There's a catchy phrase. All right, so we're nearly back on track. Sorry about that, everyone. But you're absolutely right. Newton's second law is F equals ma, where F is the resultant force. Maybe one more thing to ask that I was going to write down in the notes, and we'll see that in just a second, is the question of what does it mean for an object to be in equilibrium? That's a technical thing. It's something to do with the resultant force. So write down in the chat if you can say what it means to be in equilibrium. Yeah, you're absolutely right. That means having no resultant force. Perfect. Okay, I believe we're actually back finally, which is great. So slight technical hiccup, but we seem to be back on track. My apologies for that. Okay, fantastic. So just to review, we had Newton's second law, which says F is equal to ma. And we said that equilibrium means that the resultant force, because this F in F equals ma is the resultant force, equilibrium means the resultant force is 0. Now, I also asked a question about how we add vectors together. And the answer is if we have, for instance, a load of forces that we know about on an object. So here we've got 3 forces that we've represented with vector arrows. The way we can add them together is to put them tip to tail. Okay, so as an example, we've drawn this on the right-hand side here. Imagine that this downwards arrow is the weight. We could add this to the tension T2 on the same object by putting these arrows tip to tail. Then we could add in the other force, T1, by putting the tail of that one on the tip of W plus T2. And in this very specific situation, these forces happen to be so that you go all the way around and end up where you started. That means the result here is a vector, a force of size 0, which is exactly what it means to be equilibrium. So if you add up all the arrows together and you end up going in a loop, then what you found is that you're in equilibrium. Okay, so that's how you put vectors together. We also need to know how we can split vectors up into parts. So let's say I have a vector T1. We're going to need to know how to split this up into a horizontal part and a vertical part, so long as we know this angle here, theta. So how would I find the horizontal part here? The horizontal part of this force. What is the size of this force? It's going to be something to do with trigonometry. Yeah, absolutely right. You take the length of the vector and then you multiply by cos theta. So this will be T1 cos theta. And then the vertical part here would be T1 sine theta. Okay, perfect. Really, really nice. Okay, so that's some general stuff about forces. There's one particular force that we're going to talk about a lot, which is the weight. So the weight is the force that we feel as a result of being in a gravitational field. So let's say, for instance, we have some mass here, m, and it's hanging around somewhere above the Earth. Then we can calculate the force due to gravity, and we call this the weight. And can anyone say what the formula is for the weight? How can I calculate the weight? If I know the mass, what is the force that this mass will feel? towards the Earth. Good, absolutely right. The force is mass times the gravitational acceleration, where this g thing here is a number. You can think of it as the acceleration, and it's 9.81 meters per second squared. A kind of weird takeaway of this actually is that because F equals ma, if the only force we're feeling is the weight, then we can say the following. We can say that our resultant force is the weight, which is mg. Cancelling those m's will tell you that the acceleration of any object is always this number g. And the weird thing about this is it means that the kind of motion in the Earth's gravitational field doesn't depend on the mass. Your acceleration is equal to g, no matter how big or how heavy or how massive an object is. Okay, so that's the stuff that we're going to need to know going into today's session. Here's the spec points for the three main exam boards. So AQA, in the UK at least, we've got AQA, OCR, and EdXL. And we're really ready to get going now. So we're going to start by talking about resistive forces. And then the second half, we'll talk about rotational motion. All right. So what is a resistive force? Well, this is something we can define. It's a resistive force, or resistive forces are the kinds of forces which oppose motion. What do we mean by opposing motion? Well, I mean, imagine I have some object, and let's say it's moving in some direction with some velocity v. A resistive force is going to be the kind of force that, as a result of the motion, works against the motion, and so pushes back in the other direction. So here we've got some resistive force. We could call it R, we could call it F, we can call it whatever we like. Okay, so typically resistive forces are not things that cause, well, they cause a kind of acceleration, but we often refer to it as deceleration because it's something that will always act to decrease the velocity. So these things, rather than causing acceleration, we think of them as causing deceleration. What's worth noting, deceleration is just negative acceleration, technically. Okay, so there are two main types of resistive force, and they're pretty intuitively similar. They just depend on the kinds of material involved, the kinds of states of material involved. The first type is friction, which typically involves solids. So friction is the resistive force due to contact with a surface. So notice you need a surface here to think of something as friction. So we shouldn't include something like air resistance here. That's going to come later. That'll be drag. Right now we're talking about friction. Friction is the kind of resistive force that is due to contact with a surface. Okay. Now it can act on a moving object. If I move a block, say along a piece of carpet, then definitely we know that it will feel some kind of friction due to touching the carpet. However, friction can also act on a stationary object. For example, if I have a block on a carpet which is on a slope, I know that so long as the slope isn't too steep, the block probably won't slide down and it will just stay there still. And still the reason it will stay there is because it's feeling some kind of a frictional force, even though it's not moving. And that's a bit different to drag. So here's a kind of a different kind of resistive force, drag, things like air resistance. Drag is technically the resistive force due to motion through a fluid. So fluid is a technical term here. Fluid is a word that we can use if we want to say either liquid or gas. So if you're moving through water or you're moving through air, either way you're moving through what we call a fluid. And in either case, you would feel a resistive force. You'd feel more in the case of water, but in either case, you'd feel a resistive force. And that resistive force from moving through a fluid is called drag. Notice it's the resistive force due to motion through a fluid. So drag does not exist on a stationary object in the same way that friction does. Okay, so a classic example would be something like an aeroplane moving through literally the air. And the way drag essentially works is you have an object trying to move through a substance, but that substance is made of stuff. And when you bump into that stuff, when you bump into the particles of air, for example, by Newton's third law, they act with an equal and opposite force back on you. So as you try to move through a fluid, it tries to push you back due to Newton's third law. And that's where this resistive force is coming from. Okay, good. So that's a quick introduction to the kind of two main types of resistive force. We're going to focus on drag more now for the rest of this session. And one thing that's worth thinking about is the kinds of factors involved that can affect how large of a drag force you feel. So there are things you can do to increase or decrease the size of the resistive force you get from moving through a fluid. So if I move faster through a fluid, should that make the drag larger or smaller? Is the resistive force bigger when I'm moving fast? Or is the resistive force bigger when I move slowly? Yeah, so if I move fast through a fluid, I will feel a larger resistive force. You can feel this if you're moving along in a car, and if you've ever put your hand out the window, for example, you feel quite a strong resistive force there, and that's because you're in an object which is moving very fast through a fluid. If you just put your hand up while you walk, you don't feel a resistive force that is particularly large. So the drag increases with velocity. Okay, again, if I imagine putting my hand up as I'm moving fast through a fluid, I know that I will feel a stronger force if I put my palm in the direction I'm moving, as opposed to if I put my hand on the side and went through like this. So there's something else going on there. There's some other effect that influences the size of the resistive force I'm feeling. And that is the cross-sectional surface area. So our resistive force, our drag, increases with cross-sectional area. Cross-sectional area. Now, this term cross-sectional is kind of a fancy term for the area which is going in, which is kind of facing the direction you're moving in. So, for instance, I can imagine if I was going really, really fast through the air and I held my hand up like this and I was moving forwards, then I might notice some small amount of drag. But when I increase the cross-sectional area, when I increase the amount of area in the direction I'm moving, suddenly I would feel a much larger drag force. So I increase the cross-sectional area, I increase the drag force. Now, the third thing we need to think of is viscosity. And I'll tell you the law, but what I'd like to know in the chat is intuitively, what is viscosity? So I will tell you here, it's a kind of property of a fluid. There's a hint on the right-hand side. And I'll tell you that drag increases with viscosity of a fluid. What is this mysterious viscosity thing? It increases with viscosity of a fluid. So some fluids will give me bigger drag forces than others. For instance, moving through honey will give me a stronger drag force than moving through water. And that's because there's this kind of viscosity, which is something like the thickness of the fluid. Yeah, I really like that. Viscosity here is thickness of a fluid. If you try and move through a fluid, which is thicker or stickier, more viscous, then you will feel a stronger drag force. Perfect. Okay, so now we've learned some things about drag, and now we're going to learn about a super key concept in A-level physics, the idea of terminal velocity. And if you haven't come across this concept before, it can be a slightly surprising one. Okay, now I'm actually going to fill in the bottom of this page first, just to let you know what we're aiming for. So The terminal velocity of a falling body is the constant speed, and we'll explain this as we go. It is the constant speed that the body will reach when, so something happens here, when drag equals weight. Okay, so now this slide is going to be about unpacking this sentence. Okay, the constant speed that the body will reach when drag equals weight. So the idea here is I'm going to imagine dropping from some very large height, some object. So here I am, and I'm going to drop some object. I'm just going to hold it up and I'm going to let it go. And as a result, it's going to fall towards the ground. Okay. Now, this last sentence is saying that if we let an object fall for long enough, eventually it will fall at a constant speed. So right over here, right at the end, we're going to find an object which is falling at a constant speed. And it says because the drag equals the weight. Okay, so when something falls long enough, it gets to a point where the drag, the resistive force, is the same as the thing that's actually pulling the object down. Now, when we have two equal and opposite forces, the resultant force is zero. So that explains this constant speed thing. If you can get to a point where your up and down forces are the same, Newton's second law says you can't accelerate, your acceleration is zero, or you have a constant speed. So now we need to try and figure out why this would happen. Because when I let go of an object, initially it's not moving at all. So it will feel one force. It will feel the weight. It will feel mg. So let's jot that down. Let's imagine I drop a ball. The first thing we can say is that that body will accelerate to start with. It will accelerate due to the resultant force. There's only one force here. The resultant force, W equals mg. When I drop a ball, that very instant when I dropped it, why is there no drag force? Why is the drag equal to zero on an object I've just let go of? There's a hint on the previous page. So, if I've just dropped an object, it is not moving yet. It's got a velocity of zero. It hasn't begun to accelerate yet. And if something has a velocity of zero, then it will have no drag. Drag only appears once you're moving. Good. So initially, the body will accelerate due to the one resultant force on it, which is the weight. But that accelerating means it's going to get some speed. So the body will speed up. It will get a velocity v. So sometime later, what we've got is an object which still has a weight, mg, but it's now been falling. It's got a downwards velocity. And that means we're going to get a drag. Now let's assume we've only got a small velocity. So we've got quite a small drag so far. Where is the total resultant force still? Well, so long as the weight is bigger than the drag, the resultant force is down, and our velocity downwards is going to increase still. So we'll say, so long as weight is bigger than drag, the body continues to speed up. To speed up. But this leads us to quite a kind of a weird situation. We're going to keep on speeding up. So long as we keep on speeding up, our drag is going to get bigger and bigger and bigger. At some point, the drag will get so big that it's the same as the weight. Because if the drag wasn't as big as the weight, we would just keep speeding up until it was. So let's jot that down. Eventually then, the body moves so fast that the drag is equal to the weight. That the drag equals the weight. And hopefully you suddenly now see how we've reached that final sentence. Eventually we'll get to that speed where the drag equals the weight. Once we reach that speed, we won't accelerate anymore because there's no resultant force. So once we reach that terminal velocity, that final velocity will stay there, constant speed, and the drag will be equal to the weight. So eventually the body moves so fast that the drag is equal to the weight. That velocity where the drag equals the weight, that is called the terminal velocity. Okay, so that is the stuff there was to learn about resistive forces today. In the second half, we'll look at rotational motion, but just before that, we're going to look at some exam questions on resistive forces. So just before that, how are we all feeling? Is this feeling straightforward? Is it feeling all right? Are we feeling very confused? Are there any questions? Oh, one. Awesome. Nice. Okay, two. Awesome. Well, let's take a look at some questions. A steel ball is released from rest above a cylinder of liquid, as shown in figure 3. Okay. The ball descends vertically in the air, and then in the liquid until it reaches the bottom of the cylinder. Whenever you told a story like this and you're given a diagram, it might be worth kind of checking that you understand the story in the diagram. So it's released above the liquid. Okay, steel ball released here. That's in the diagram. Okay. The ball descends vertically in the air. So descending means moving down until it hits the liquid. Okay, yeah. And then it keeps descending until it hits the bottom of the cylinder. Okay, seems to make sense. Figure 4 below shows how the velocity of the ball changed after it was released. Okay, so we have a graph of velocity here against time. Describe and explain how the acceleration of the ball changed after it entered the liquid until it reached the bottom of the cylinder. And they're going to assess the quality of our written answer. Now, this is a really great question for understanding terminal velocities. Notice that there's 6 marks here, so it's going to be quite a long answer. And notice that it's a describe and explain question. So there's 6 marks available, describing and explaining. Probably we need to describe about 3 things and give an explanation for each of those 3 things. And altogether, that would be 6 points that we've made that would give us about 6 marks. Okay, so let's take a look at this diagram again. And you might notice that there do seem to be a kind of 3 distinct parts to this graph. There's the start here where we have linear motion. We have a straight line. So let's call this section 1. We're going to deal with section 1 first. And then there seems to be this kind of steep backwards bit here. Let's call that section 2. And then things seem to be going really flat at the end. Let's call that section 3. We're going to describe each of those sections technically now, and then explain what we've described. Okay. Describe first how the acceleration ball changed. Okay, so they want us to describe the acceleration. What can we say about the first section? Well, in the first section, what is acceleration in a velocity time graph? Okay, key question. This is a super key one. How can I figure out acceleration from this graph? If I give you a graph of velocity against time, where's the acceleration in this? It's the gradient. Good. So this is a really key principle in all of this question. Acceleration is the gradient of this graph. Nice. Okay, yeah, which you would get by differentiating. Absolutely right. So if we look at section 1, we see a constant gradient. So in section 1, we can say until until the time t0, we can say that the acceleration is constant. And then a key question I have is, why is the acceleration constant here? What does that tell us about the motion? So until time t0, the acceleration is constant. Okay, but let's take a look now back at the picture. And we'll say, well, this is a bit weird. Why should the acceleration be constant? There's a weight on this object, but shouldn't there also be a drag? After all, it's moving through the air. Well, this is a very small object. And so because of the thing about, we were talking about the area of an object, because of the area of the object being very small, we can essentially ignore the drag for this very small object over short enough distances. So in section 1, we will say this. We'll say, because the drag can essentially be ignored due to small area in a non-viscous fluid. Okay, so now let's look at section 2. And section 2 is pretty different. First of all, we notice that the acceleration has changed direction. Before, the acceleration was given by this positive gradient. Now afterwards, we've got a negative gradient. So the acceleration has changed direction. Well, we know that initially the acceleration must have been downwards. So this change of direction, this going to a negative gradient, means that once the ball hits the fluid, it must now be the case that the acceleration is actually upwards. Okay, so here's a key question. If the acceleration on an object is upwards, and there are two forces on it, the weight and the drag, that must mean that the drag is in fact bigger than the weight here. So that's a kind of crazy thing. We're going to be coming in from the other direction here. So let's jot this down. First of all, we just need to describe. And to describe what happens to the acceleration, we just need to say, just after t0, we can say that the acceleration changes direction and points upwards. This must be because the fluid is so viscous that the drag is in fact bigger than the weight. So here we have the drag being bigger than the weight. Now, let's take a look at section 3. At section 3, we have essentially no acceleration. We seem to have a kind of constant velocity. And they're going to be looking for a key word here. What word can we use to describe this constant velocity that the object eventually reaches? Exactly. So we'll get a mark here for mentioning terminal velocity. So in section 3, this section at the end, eventually acceleration tends to 0 as velocity tends to a constant terminal velocity. And why is this? This is because the drag causes velocity to decrease until it is the case that the drag equals the weight, at which point we would have a constant velocity. Absolutely right. Good. Okay, so hopefully that's all making sense. The second half of this section is on an essentially different point, a different topic. Maybe the thing that connects both of these halves of today's session is the idea of equilibrium, the idea of things being balanced. So now we're going to talk about rotational motion and moments. So we're going to start by defining a moment. So a moment is a kind of the turning power, the turning effect of a force, and we can define it like this. The moment of a force about a point is, in intuitive terms, the rotational force. Now, that's just an intuition. That's not a technical thing. The technical thing is moment, and it is given by the following formula. M equals Fx. Now, F is the force. M is the moment due to the force. What we need to be careful about is what we mean by this x here. This represents a distance, but not just any old distance. It represents the perpendicular distance. Perpendicular distance to the point. So let's see what we mean by the perpendicular distance by looking at a very explicit example. Okay, so if you take a look at this object on the right-hand side here, it is experiencing a force called the weight. This weight is pulling down, and we can draw the line of action of the force. So that's what we've drawn here. We've drawn a line of action of this force. And then the perpendicular distance is the distance from a point, the shortest distance from a point to the line of action. So it wouldn't be this distance here or this distance here. It would be the shortest possible one. We call that the perpendicular distance because that distance will form a little right angle with the line of action of the force. So here, if we wanted to find the moment about this point here from the force W, we'd need to use this distance here as x. Good. Okay. So we'll look at some examples of calculating moments. But first of all, we're going to mention a special type of moment called a couple, okay, or a special type of moment called a torque, which is the type that is caused by a couple. So a couple is specifically a pair of balanced forces applied at different parts of a body. So couples are very interesting. Let's just put this, parts of a body. Couples are very interesting because they make something very clear very quickly, which is that force equilibrium isn't the only important type of equilibrium. So let's say I have two balanced forces on an object pushing in opposite directions. The resultant force is zero. So the acceleration should be zero of the entire body. But that misses something, because if you apply equal and opposite forces at different parts of the same body, you won't get the whole thing to move to the left or to the right, but you will make it rotate. So a couple has force equilibrium, but not moment equilibrium. That's the key thing. Now, when we're specifically talking about couples, we say that the moment caused by a couple, so moment of a couple, is what we will call a torque. Okay, perfect. So now why this conversation about couples gets across a key point, which is that we need a new type of equilibrium, which is having no rotational effect. And so just like we have the idea of a resultant force being zero, we're going to need to be able to talk about whether the resultant moment on an object is zero. So what is the resultant moment? We need to define this. It's like the total effect of all the different turning forces on an object. And we can define it like this. The resultant moment about a point is the difference between the sums of clockwise and anti-clockwise moments. Okay, that's a sentence that looks a little more complicated than it actually is. So let's take a look at an example. Let's take a look at this diagram on the right-hand side. And let's imagine we want to take moments around this point here. So this is going to be our point. Well, this 8 Newton force, we could then ignore because we're taking moments about the point where it acts. It has no distance. That x in the formula for moments, remember, moment is force times distance. Here for that 8 Newton force, that distance is 0. So there are 2 moments to look at. There's the moment due to the 3 Newton force. This one is pushing things clockwise. And then there's the 5 Newton force, which is pushing things anti-clockwise. Okay, so let's look at the definition. The resultant moment about our point should be the difference between the sums of clockwise and anti-clockwise. The resultant force, yeah, exactly. So this is another one of those kind of funny examples where the resultant force is clearly 0. We've got 8 down and 8 up. But that doesn't capture the whole picture because there's still a question of whether it may not move upwards or downwards, but there's a question of whether it will still rotate, whether the forces are balanced in the clockwise, anti-clockwise way. But you're absolutely right. The resultant force is 0. But now we're asking about the resultant moment. So the resultant moment is a difference between the clockwise and anti-clockwise forces. So let's look at it. The difference between the clockwise and anti-clockwise moments, sorry. So the clockwise moment here is a force of 3 newtons at a distance of 2 meters. So we have 3 times 2. But it's the difference between that and the anti-clockwise moments. So what are the anti-clockwise moments here? Well, we have a 5 Newton force at some distance d away. So we have 5 times d. So altogether, we can say that the resultant moment equals 6 minus 5d. Nice. Okay, so now let's look at the principle of moments. And this is going to be just like the principle that says you have no acceleration when your total force is 0. Okay, the principle of moments says that a body is in, and here's the key bit, rotational equilibrium. Rotational equilibrium. If the resultant moment is 0. If the resultant moment is 0. So this is just like saying an object is in equilibrium if the resultant force is 0. It's in rotational equilibrium if the resultant moment is 0. And just like if the resultant force is 0, we have a constant velocity. If the resultant moment is 0, you'll just keep on rotating at the same rate. If you weren't rotating to start with, you'll never start rotating. Okay, so let's apply this idea to the diagram on the right-hand side. Let's say that I tell you that this object on the right-hand side is in rotational equilibrium. That gives me an equation. It tells me that the resultant moment must be, well, it says it here on the left-hand side, the resultant moment must be 0. So putting together all these ideas, you could actually figure out that distance d. You could figure out what that distance d needs to be if this thing is going to be in rotational equilibrium. And let's do that now. If the resultant moment is 0, and the resultant moment is 6 minus 5d, then we must know that 6 minus 5d equals 0. You could rearrange for d. That would say 6 equals 5d, or in fact that d equals 6 over 5. And actually, if you chuck that in a calculator, that is 1.2 meters. So there you go. If you know something's rotating at a constant rate, you can figure out some of the other properties of that object, like some of its lengths. Okay. So there is one more concept that we're going to look at before we do some practice questions. And this is kind of a funny bit, really. We are now going to talk about the same point on an object in two different ways. So again, I'm actually going to fill in the bottom of this slide first. I'm going to introduce 2 points to you on an object. And the punchline is going to be that these 2 points are in the same location. Okay, so we have 2 points that are in the same location. So they're the same point. What are these two definitions? Okay, the first is the idea of center of gravity. The second is center of mass. So the center of gravity is the point on the body. So the center of gravity of a body is the point at which the weight of the object acts. The object acts. So this is kind of a funny thing. We're often used to in physics thinking about an object as a point, and then the weight acts at the point where the object is. But often we actually need to think about extended objects like rods or pieces of paper. And we need to draw the weight as acting somewhere on that rod or piece of paper. So for instance, with a uniform rod, so a rod that has the same density all the way along it, then we wouldn't think of the weight as acting on the right-hand side or on the left-hand side. We'd think of it as acting in the middle. So that is the center of gravity. And similarly for a piece of paper, we would think of the weight as acting right from the actual center, like geometrically, of the object. If the density is funny, then that can throw off where the center of gravity will be. Okay, the second concept is pretty similar, but it is different. It's the center of mass. So the center of mass of a body is the point at which a force would not cause rotation. So let's take a look at this rod that we've written down. If I give it a kick at the bottom, first of all, I'll send it off to the right probably, but also I'm going to set it spinning. However, if I give this rod a kick directly in the middle, then which way would it spin? Clockwise or anti-clockwise? It wouldn't know how to choose. And in fact, it wouldn't spin. It would just kind of go straight to the right. No problem. So there's the point at which a force wouldn't cause rotation. As you can see intuitively, in a uniform object, it's the middle. And it's the same for the center of gravity. The weight acts through the middle. Now, it turns out that even when you have non-uniform objects, so really weirdly distributed masses, something that you can always rely on is that these 2 points will be in the same location. Okay, great. So how is that sounding? How are we feeling? Okay, so for the last part, just take away the following sentence. Sometimes the examiner will tell you about the center of mass. Sometimes they'll tell you about the center of gravity. And your takeaway just needs to be that those are the same point. And in a uniform object, it would literally be the middle. We'll actually look at an exam question where we have the center of gravity being somewhere other than the middle because it's a non-uniform rod. So that might help. So there are these 2 phrases, but you can think of them as the same. Okay, well, we'll see an example now where the center of gravity is in a kind of funny place. Okay, so figure 2 here shows an apparatus used to locate the center of gravity of a non-uniform metal rod. Okay, so here we have this rod, and you can see it's kind of thicker on the left and thinner on the right. And that's the reason why in this case, kind of the gravity acts slightly kind of on the left. More of the mass is actually on the left than on the right. Okay, and what we're going to do is figure out exactly how far from the leftmost point, the center of gravity is. We're going to figure out where the weight is acting as if where it is as if the weight was acting. Okay. So this is a conversation, this is a question which is a lot to do with equilibrium. And the first thing they ask is, state two conditions that must be satisfied for this rod that they've drawn here to be in equilibrium. Okay, what two things need to be zero for us to be in full, proper, every kind of equilibrium? I'll state the first one, but we've learned a new one. So the first one is, we know that the resultant force must be zero. Resultant force must be zero. And that'll be newtons. Well, what's the second thing that also needs to be zero? Good, the resultant moment also needs to be zero. Perfect. Resultant moment equals zero. Now, what are the units of moments? We'll come back to this later, but moment was equal to force times a distance. So that's newtons times meters. Let's just put that there for an extra bit. Good. Resultant force must be zero. Resultant moment must be zero. And we know, if we know, well, we're told this thing is in equilibrium. In real terms, it seems like this thing is probably just staying still. That would be one way to know it was in both kinds of equilibrium. Okay. Wire Q is attached to a Newton meter so that the force the wire exerts on the rod can be measured. The reading on the Newton meter is 2 newtons, and the weight of the rod is 5 newtons. Calculate the force that wire P exerts on the rod. Okay, so let's take a look. We have wire P over here. It must be exerting an upwards force. We have wire Q over here. We were just told that that is exerting a force of 2 newtons because that's the reading on the Newton meter. So we have 2 newtons over here. And then we have the weight of the rod. And the weight of the rod here is 5 newtons. Okay, so what must P be? Well, the first kind of equilibrium says the total force is 0, which means that P, which is upwards, plus 2, which is upwards, must balance the 5, which is downwards. So that tells us that P here is 5 minus 2, which is 3 newtons. Good, absolutely right. And now they ask us to find the distance d. Now there's a big hint here. The first part of the question made us think about both kinds of equilibrium. We've already used force equilibrium. We're probably now going to have to use rotational equilibrium. Okay. So we're going to try and find the distance d. We're going to take moments about somewhere. It's usually handy to take moments around a place where one of the forces acts. That way you can discount the force. So here we can ignore the force at wire P. Now we need the resultant moment to be 0. So we need the clockwise to be the same as the anti-clockwise. What's the clockwise? Well, we have 5 newtons down multiplied by this distance d from the point. That needs to balance the anti-clockwise moment, which is this 2 Newton force at a distance of 90 centimeters. I'm putting things in centimeters, so I'll get things out in centimeters. Okay, so we can rearrange for d. D will be 2 times 90 divided by 5. And if you chuck that in a calculator, you'll get 36. And remember, we said this was centimeters, so this will also be in centimeters. Great, okay. So now we've got a couple of final questions before we wrap up. We're asked to define the torque of a couple. Okay, the torque of a couple is the moment due to a pair of equal opposite forces which could in principle have been at different places. Now we're asked to explain why moment of a force and torque of a couple, and we've seen in both cases their moments, have the same unit Newton meters. So why is this? Well, first of all, let's just mention both are moments, as we mentioned above, meaning they are given by a force times a distance, giving newtons times meters. Good. Okay. Figure 4.1 shows an irregular shaped metal plate of constant thickness that can swing freely about point P. Okay. The weight of the plate is 6 newtons. With the plate in the position as shown in figure 4.1, calculate the clockwise moment of the weight. Okay, through point P. Well, here's point P. Here's the weight that we want to calculate the moment of. Remember, what we need to do is draw that line of action of the force, and we need to find the distance between that line and the point P. So that's going to be this distance here. And we would seem a bit lost, except that they've actually given that distance. They've just written it further down here. That distance is 0.4 meters. So altogether, the moment is the force times the distance. So that's 6 newtons multiplied by 0.4 meters, which will give you 2.4. And indeed, the result is in Newton meters. Okay. Finally, we're asked to explain why the moment of the weight reduces to 0 when the plate reaches the bottom of the swing. So this is a really nice question. So this plate is going to swing around. After all, it's currently got a net moment. But then they mentioned that when the plate reaches the kind of bottom of its swing, and this is quite hard to draw, it's going to look something like this. Then, when it reaches this bottom of the swing, and so this is our center of gravity, by the way, the place where the weight is acting, then suddenly the moment's going to be 0. And why is that? Well, once the thing is at the bottom, the weight is going to be acting through a point which is directly underneath the point around which we were swinging. So the idea is that when we're right at the bottom of the swing, the line of action of the weight goes through the point P, and so the perpendicular distance is 0. So the line of action of weight passes through the point P. And consequently, the moment given by force times a distance of 0 will itself be 0. Okay, so hopefully this is all making sense. You should now, we kind of did 2 things in this session. You should now be able to explain the effects of resistive forces on bodies in motion. You should be able to define moments and centers of mass. And you should be able to determine if systems are in either this rotational kind of equilibrium or this translational kind of equilibrium. So that's the end of all the stuff that was in this web class to show you. Let me know if you have any questions. While I'm looking at any questions you put in the chat, I'm going to let you know about what we're doing on the SnapRevise website. So this web class we did today, I'm doing this with SnapRevise. And I do a lot of these kinds of web classes on SnapRevise, but also there are courses that you can take part in on the SnapRevise website. So I'm just going to tell you a little bit about that now. Okay. And I will keep an eye on the chat for any questions. Okay. So hopefully you can now, let me just check. Yes, great. You can see my screen. Okay. So I'm on the SnapRevise website. I'm actually looking at some stuff on Moments here. Yeah, just type the question in the chat. Go for it. So I'm on the SnapRevise website here. And I'm lucky enough to currently have the AQA A-level physics course. And I'm just going to show you a bit of what's going on here. So there are we've made an entire series of video courses. So you see all of these subheadings from your A-level physics course. And for each one, we've made a series of videos. We made a video course. And it's kind of interestingly set up. So you can take quizzes in each of the in each of these topics. So I've already taken the quiz here for this section on reflection, refraction, and diffraction. And when you take the quiz, what's quite interesting is then the video course is going to be kind of built around you. So what's the idea? Well, Here are my courses on the left-hand side. Here are my videos, which I can watch. But based on how I answered my diagnostic quiz at the start, actually, I can see that there are certain parts of this course, certain parts of the videos that are more important than others. For instance, I got a question on planar wavefronts right. So it's highlighted in green, and I don't need to necessarily focus my time on that part. So this video is showing me that I actually just need to spend time on this orange part at the start if I want to most efficiently correct the things that I currently didn't know so well. Okay, so this is a video course, and it's built around how you answer your various quizzes. We also put down some videos where we show ourselves going through exam questions that we've written to show you how we would think about answering them in a real exam situation. And if you're not so keen on video stuff, then also we've been writing some typed stuff. So we have a series of exam questions again that we've been writing. And so we call these the exam packs. You have them for each topic. And in each case, you can choose the difficulty level. You can take a look at the question and flip and take a look at our solution once you're ready. Okay. Finally, if you like to read from revision guides, we've also been writing revision guides for every single part of the A-level physics course. So you can take a look at these as well. Okay, so we'd love to see you over there at Snap Revise. Let me know if there's any questions about that too. Just taking a look here. So if the line of action of the weight passes through the center of the mass, then the perpendicular distance is 0. Yeah, that's exactly right. And that's the reason the moment was 0 in that last question. And that is why the potato didn't undergo rotation. That is why the moment on the potato would be 0 at the end. I also never thought of it as being a potato, but I guess it is kind of potato shaped. But you're absolutely right, yeah. Except that it may have still been rotating, but just at that point where it swung so that the center of mass was under the point, at that point, there was no moment. It could have still been swinging, just like you can have no net force and still be moving. The point is it had no, when you have no net force, when you have no resultant force, you have no acceleration. You'll keep moving constantly. In the same way, just at that moment, when you swing under the point, your rotation will be staying at a constant rate. Okay, great. Okay, hopefully that all made sense. Thanks very much for joining me. I actually have more web classes to do now on the Snap Revise website. So I'm going to go over there and do those now. And see you all next time. Great. Thanks very much. Bye.